In this video, I'll start our discussion of vector math. Some quantities have magnitude in units. For example, we could have 20 years, 15 meters, etc. So these have a quantity and a unit associated with them, or an amount and a unit, or what we might call a magnitude and a unit. Speed, for example, is one of these quantities. So we might report speed as 15 miles per hour or 20 feet per second. Velocity has direction, also has direction. So we may have to say the velocity is 20 miles per hour toward Phoenix. So we'd like to be able to represent these things that have magnitude, units, and direction a little easier. So we represent them as basically just these nice straight arrows. So the arrowhead and the line provides a direction. The length of the line provides a magnitude. So this is the magnitude. This arrow and this line indicate the direction. Now in the case where the vector represents a force, because force is a vector, is the line of action of the force. So the force may be applied right here. So perhaps we have a little block here that this force is being applied to. But the line of action of the force actually extends that way and that way to infinity in both directions. Now, I'm bringing this up here, but the importance of this concept will be made clear when we discuss moments in Chapter 5. So for now, just try and remember that this line is called the line of action. Alright, so let me show you how to do vector addition using this graphical representation of vectors. So let's assume that we have vector A. Now the book uses bold letters to indicate a vector. I'm going to use this nomenclature with a little arrow over the symbol to indicate that that is a vector quantity. Vector A is 3 newtons at an angle of 70 degrees from the horizontal. So 3 newtons. I want to add to that vector B. Vector B is 2 newtons, a little shorter, and an angle of 20 degrees from the horizontal. So, in order to do vector addition graphically, what we do is we take one of these arrows and put its base at the head of the other arrow. It doesn't actually matter which of the two we choose. In other words, we can put this base at this head or this base at this head. So when we do this graphically, what we wind up with is something that looks like this. So this is the case where I added the 2 newton to the 3 newton. Or I could equally have done this. And that's the case where I put the 3 newton on top of the 2 newton. Okay, both of those are equivalent. The vector that runs from this point, which is where the two tails start, to this point, which is where the heads meet, is the sum of the two vectors. So C which equals A plus B, is this vector right here. Now, determining the actual magnitude, and more importantly, or just as important, the direction that this arrow is making relative to some point, our reference frame, for example, the horizontal line here, requires a bit of trigonometry. So there are two equations from trigonometry that you should commit to memory if you haven't done so already. So let's write those down real quick. So if I have a triangle, an arbitrary triangle, that have sides A, B, and C, and angles alpha, which is opposite A, beta, which is opposite B, and gamma, which is opposite C, we can write the law cosines, which states that C is A squared plus B squared minus 2AB times cosine, right? Depending on which you have. You have A and B, or A and C, or B and C. They're all the same, okay? We can also write the law of sines, which states that A over the sine of alpha equals B over the sine of beta equals C over the sine of gamma, right? So here's the law of sines. Here's a couple different representations of the law of cosines. You should definitely have these memorized very shortly in this course. All right, nonetheless, if we go back to our particular problem here, let's blow it up a little bit so we can see it. And I'm going to use the top triangle. So I've formed this parallelogram, and I can use either triangle here to deduce this information. So let's blow it up. Here's our 3. Here's our 2. Here's the add them together vector that we're looking for. Right? Now, we know that this angle is 70 degrees. Right? That means, I'll use a slightly different color here. That means that this angle is 70, right? So from here all the way back over here, this is a straight line, has to be 180. So right here, we have 180 minus 70. We also know that this angle right here is 20. So if we go back now, and so I'm going to erase that. Now that you see that, we get that, that'd be 180 minus 70 plus 20. 180 minus 70 plus 20 is 130. So we actually know one of these internal angles. We also know this distance is 3 and this distance is 2. So we can say they're both in newtons. And now if we look carefully at the law of cosines, and we call this C, we have the two opposite sides and the angle between them. That's all we need to determine the length right here, right? So C, this length, is equal to the square root 2 squared plus 3 squared minus 2 times 2 times 3 times the cosine of 130. Now be careful, when you calculate the cosine of 130, you're going to get a negative value here, okay? So be sure you keep all your signs straight. 130 cosine is actually minus 0.6427. Nonetheless, if you do this full calculation, you'll get a value of 4.551. So now we know the magnitude of C. It'd be nice also to know this angle right here, right? What's this angle? Well, it's actually 70 minus this little angle right here, which we'll call beta. 70 minus beta. How can we determine what beta is? Well, sine of beta under 2, right? The length of a side over the sine opposite equals the length of this side, which is 4.551, over the sine of 130. And of course we could flip that around if we wanted to, right? We could say sine of beta over 2 is sine of 130 over 4.551. Nonetheless, if you do the math, you'll find out that beta is 19.67 degrees. That means that theta is 70 minus 19.67, or 50.33 degrees. And this, of course, we should put units. 4.551 newtons at 50.33 degrees from this horizontal line. So now we've added vector A and vector B. What if we want to do subtraction? So again, what if we had vector A, which is equal to this vector making 30 degrees. Let's call that 3 newtons. And B is this vector, which I probably didn't do a good job making 20 degrees, and let's say it's 3 newtons as well, right? Alright, so what we want to calculate is A minus B. Well, it turns out that we can multiply a vector by a scalar with no problem at all, right? So let's multiply B by minus 1. And so that makes this equivalent to A plus minus B. So what's minus B? Minus B, right, is the same vector, just pointing in the opposite direction. That's still 20. The length is still 3, right? So A minus B is the same as A plus minus B. So now we can write that. So we've got 3 newtons going this way at 30 degrees. And then coming back, we have 3 newtons, right? So right in here would be our A minus B vector, right? So right here. So that vector goes that way, that vector goes that way. 3 and 3. It takes a little bit of effort, but again, using the law of sines and law of cosines, you should be able to determine what this difference is. Okay? It's also important to recognize if we can put two things together, we should be able to take something apart. So for example, if we have a single vector, let's say it represents 10 newtons of force, and it makes 30 degrees with the horizontal. We may like to know, well, what vector at 150 degrees from the horizontal plus what vector at, let's say that's 0 degrees from the horizontal do I have to add together to get this vector? Well, let's do that. So here's our 10 Newton vector making 30 degrees, right? Here's a vector right here that makes no angle with the horizontal, and here's one that makes 150. So we add one that makes 150 plus one that makes no angle, and we should get back to here, right? So we're still doing this tail head addition to get to the original vector. We've got a little bit of work to do. So originally this was 150 degrees. That means that this is 120 degrees. If we think about it for a second, we should recognize that if this was 30 here, then this is 30, which means that, lo and behold, this is 30. That means this is 30. And now we can say, what is the magnitude here? And what is the magnitude here? So here it's actually not too bad. Oh, sorry, this is 10 right here. So 10 over sine of 30 equals x over sine. That's pretty easy. X equals 10 newtons. Furthermore, that equals y for sine of 120. And if you do the math, y is 17.32. Okay, so we've seen that we can represent vectors graphically using this arrow approach, that we can graphically add these vectors by using this tail to head formulation, right? We can subtract vectors using the same idea, where we just have to put a minus sign in front of one of the vectors that we're in front of the vector that we're subtracting. We can do this for multiple vectors. And we can also, very importantly, take a vector and decompose it into two vectors that are going in directions that we've selected, okay? We could conversely do this the other way, right? We could also say, look, I want a vector of magnitude y and magnitude x. Tell me what directions those two vectors have to point in, so when I add them together, they give me this vector of 10, making an angle of 30 degrees with the horizontal.